In this video, I would like to talk about one of the most important applications of what we've just been learning, which is electron guns. Sounds pretty scary, but until recently, pretty much every house in the world had an electron gun in it. It was an old-fashioned television. What you had was a vacuum glass container with an electron gun down the bottom that would fire out a beam of electrons, and then there'd either be a magnetic or electric field over here to direct it. So the beam of electrons would come out and be directed very rapidly to one side or down to the other side. And the front of the screen over here was covered with phosphor, which would flash and emit light wherever the electron beam hit it. And the electron beam would be scanned backwards and forwards many times a second, and you change the intensity of the electrons, and that will give the picture at the front of the TV. Nowadays we tend to use flat screen TVs, though apparently a few computer gamers still like these ones because they're faster response time. But there are many other applications of this. One of the scariest applications is in producing atomic weapons. What you can produce is not a beam of electrons, but a similar process producing a beam of uranium ions. And once again, you can deflect them using an electric or magnetic field. So the different isotopes, they all have the same charge, but they have different amounts of mass, go different directions where you can collect them and get the uranium-235 as opposed to the uranium-238. This is a technology first pioneered in the Manhattan Project back in the Second World War. More peacefully, you can once again get a beam of ions, let's say carbon ions, and once again you can apply an electric field sideways across it, and that will give an upward force, an acceleration that depends on the mass, and you can separate out the different masses, the different chemicals within it. And this is a mass spectrometer. You then have a sensor over here to measure how much of things at different weights come through. And this is incredibly useful in all sorts of fields: chemistry, medicine, archaeology. For example, this is how you work out the ratio of different isotopes of carbon to allow you to carbon date things. So once again it has this charge gun over here. You can also use them for space propulsion and ion drive. So now you get your ion producing xenon ions, fly them out at a huge speed, and that acts like a rocket and allows your spacecraft to go the other way. And this is an ion drive, for example, on NASA's Dawn spacecraft that's currently touring the asteroid belt. So these are very useful things. How does it work? Well, let's focus on the electron gun. Ion guns use different but fairly similar processes. The way an electron gun works is something like this. It has to be done in a vacuum, otherwise the electrons will just hit atoms and get mopped up too soon. You start off with a point which is heated up, and as it's heated up, electrons fly out just because the thermal motion knocks them out of the spike. Left to themselves, they'd wander around and probably fall back. What you then have is, some distance away, you have an anode. So this is given a strong negative voltage, this is given a strong positive one, which gives positive charges here, which means there'll be an electric field pointing this way. As the electrons have a negative charge, that means they will accelerate this way. Now left to itself, the electrons will then fly over and hit this and wipe out the charge you produced. So what you also need is some sort of focusing device, and what you typically have is a metal cylinder, something like that, and you put that at a more negative voltage than the cathode slightly, so that means the electrons fly out and are focused, and so mostly go through the hole. Once they're out, there's no more electric field, and they can fly off and hit their target or get sorted or whatever you want. How fast are the electrons going in a situation like this? Well, we can work this out using energy calculation. The voltage in a typical TV is about 20 kilovolts between the cathode and the anode. So that's our potential difference. Now we know that the change in energy is equal to the charge times the change in voltage. We also know that our electrons are starting off not moving very much and end up going very, very fast. So that's going to turn into their kinetic energy, a half mv squared. So what we'll find is that rearranging this, that comes to 2q delta v over m equals v squared. So taking the 2 up to the top, taking the m down the bottom. Then we'll do the square root. And if you plug the numbers in, that comes out as about 8 by 10 to the 7 meters per second. That's 25% of the speed of light. So you may think relativity is for science fiction movies, but no, they get speeds of a good fraction of the speed of light in a typical old-fashioned TV. Another way to calculate it, more complicated, but it might give you some insight, is to look at the force. You've got an electron sitting in an electric field, and therefore there's going to be a force applied to it. And we know that the force is equal to the electric field times the charge. The electric field is the voltage divided by the distance here, call that d. Simply because that's the definition of voltage. Voltage is field times distance. Oh, that's times q all here. And that of course equals ma. So you can use this to work out the acceleration, which comes as a whopping 7 by 10 to the 16 meters per second squared. Yeah. Eat your heart out, sports cars. That is one hell of an acceleration. Doesn't last very long though. Just from here to here, and they fly out in a tiny fraction of a second. So that's how electron guns work. Very useful technology.